Good, all ready to go, I think. Welcome back. In Unit 8 of COMP526, a short unit, we'll look at error correcting codes. It's a nice little construction that we'll look at the end of this. There's a few nice additional lower bounds that fit into this. And it's a nice way to complement the longer compression unit. So I think you will enjoy this one. And the main construction is also an easygoing exercise. So without further ado, the learning outcomes for this unit are to understand this context where when we talk about communication in computer science, we usually mean two machines talking to each other, but they still make errors in the communication medium, and we have to work around those. And there's some standard constructions how you can achieve this. You will always have to live with the fact that there's a small probability of failing, but what we will be able to do is bring that probability down by using specific codes that can correct certain small errors. We'll look at certain examples. Block codes is the general theme. Hamming codes is the concrete one that we will look at. And we will we'll argue a little bit about when or when not such a code is applicable. The unit has 3 short sections, a bit of introduction, and then the lower bound side first this time, and then the Hamming codes as a way to achieve some parts of this. So what are we talking about? I put this title Noisy Communication, but it's maybe true that communication is almost always noisy in some sense. If you think about humans, when we talk to each other, there's all sorts of things that can go wrong. I'm sure you know all about these. And how do we cope with that? What ways have we found to work around all of these different problems? I think humans are quite good at sensing whether the other person's following using our mirror neurons. We try to see what the other person's reflecting in their faces well before they ask pardon. And so often we automatically slow down, speak up, try to say things in different terms. When you're asked to repeat something, maybe you don't say it word by word in another way. If you feel the other person maybe is not English as a first language person, maybe you try to rephrase it. All these things we do almost automatically, but there's quite a lot of things we do to try to make communication a bit more reliable. And we'll see some of these also pop up in a machine context in slightly different forms. Another thing is that if you read out this sentence, maybe you can try it for yourself. It's remarkable how much redundancy is built into natural language text. We looked at this in the last section in the last unit. I showed you this example of compressing the text of the Bible down to a quarter. That was one way of saying, oh, 3/4 of the Bible are just repetition. And maybe this is not so much to say about the Bible than about English as the translation of the Bible. And the flip side of this is, even if I jumble around some characters, you can still read it, and assuming that this is an English sentence, you will automatically figure out what it was, even though there's quite a few characters wrong or missing or jumbled around. So to make this a little more precise, we can do 2 different things, and if you think about them, they're quite distinctively different. We can detect errors and we can correct some errors. In this sentence, we're pretty good at quickly spotting that something's awfully wrong if that doesn't look at all like English. But this is beyond repair. There's too much. I mean, you can only make wild guesses what that could have meant. Whereas in this second case, or in this box, if there's smaller errors, we kind of find the closest possible legal English sentence. And this is something that our brain does automatically because we're so much trained to reading. And well, there's this child's game where you whisper something in one person's ear and the person has to say it to the next person's ear. And if you've gone through a row of 10 kids, then what comes out has nothing to do with what the first person said. It's known under different names. I don't know. What do you know this game under what name? Chinese Whispers? Yeah, I think telephone is the American version. And yeah, some similar term to Chinese Whispers is the German one. So somehow it's associated with Chinese, which is probably just because it's very foreign for Europeans. So we try to automatically correct something that we hear to something that makes sense to us, and we are very eager in doing that, sometimes too much so. Okay, so that's for communication, but what we'll take out from this into the technical context is this distinction. Detecting errors is not the same as correcting them, and clearly the second is tougher. For computer communications, we'll usually abstract them to a channel. So that's just something that transports information from one end to another. For computers, these are usually cables, or it's some sort of radio signal. We'll always pretend we transmit some binary string. If not, then you know from the last chapter how to encode that in binary, so it's not really a restriction. And our model will be that this channel occasionally flips a bit. It turns a 0 into a 1 and a 1 into a 0. This nicely fits a scenario where the channel has a well-synchronized clock. So the channel can be in two states. It can be high or low, and then you read out the state of the channel in regular time intervals. And we assume that this time is not tampered with, but maybe the channel sometimes is ambiguous, and then it's jumping into the right in the wrong direction. That's the model of noisy channels. You can make the game more challenging by looking at different channels. You can also assume that maybe sometimes there's an additional bit squeezed in, or that other types of errors occur where a whole burst of bit flips is more likely. We'll keep it very simple for this one. So there's some probability that each individual bit is flipped. We think that this probability is not too big, but it has to be dealt with because it occasionally happens if you transmit a long message. So we're trying to look for a robust code, a code that achieves good communication, even though this channel isn't perfect. So we definitely want to detect errors so that we can just ask the person to say the same thing again, ask the computer to retransmit that package. Sometimes it's also convenient to correct the errors if possible, so we build in more redundancy. Then we can avoid retransmitting something. And there's also scenarios where retransmitting is not really an option. If you send something into outer space and it sends messages back to Earth, telling that thing to just send it again might not even be possible because you can't reach it. It's only a one-way communication channel. So both are equally important. Depends on the scenario if detection is good enough. For both, we will need some form of redundancy. I think this is intuitively clear. If every possible bit pattern that you can take out of the channel means something different to you, then there's just no way you can know that an error was actually meant something else and is not the message that you received without an error. So you need to send a few more bits than the actual payload, than the actual message. And we would like to reduce this additional number of bits, the redundancy. Now, because you probably don't know much about this, the next question is just asking for your intuition. And it will be, I think, insightful to look at this again later. So suppose, very simple scenario, you want to send 100 bits across a channel, and say with some percentage, there's a 5% chance that every bit gets flipped. Let's say a 1% chance, then we expect one error. How many extra bits do you think, just a gut feeling, what do you think? What do you think how many bits we need to send on top of these 100 to detect that something went wrong? And specifically that a single bit was flipped. That's the error that we're looking at. Again, miraculously, more people voting than are in the room or on the live stream. But I don't want to discourage watching this live stream together in a room. Maybe that's what's happening. It's a very lovely idea. All right, let me just show this. The guesses vary wildly from 1 to 100, 200. And I don't want to comment on this much. I have a similar question. So this was just for detecting the errors. Now the same question, but now I want to be able to correct this error. Okay, so same scenario otherwise. But in case your code detects that there is an error, I want to be able to also fix that one. Again, unless you've seen something about this, there's no way you could know, so you just guess. I think the main purpose of these questions is if you look back at your answer from before in an hour, might be interesting for you to see. Yeah, we had something like 29 last time. Let me show it. Again, I won't comment on this point. Again, widely different guesses. The only thing that probably should be clear, the number you type for the second question should be at least as much as for the first question. If you can correct an error, you've already detected that there is one because you know what you received, you know what you produced, and if these are different, then there was an error. So that's kind of obvious. Anything beyond that, at this stage, you can't really know from anything I told you, at least.